an extended version. There is some additional experimental results and some unpublished ones as well. So it's a good occasion for you to stay still. So what did we do in this experiment? We essentially revisited a well-known physical process, a cascade decay of an atom through an intermediate level in a context or at an angle that was not really looked at before. And cascade decay reminds us of the early days of quantum optics. Indeed, the very first experiments on the violation of Bell inequalities, they were performed using atomic cascades as sources of polarization entangled photons. So in those experiments, however, the excitation of the atom was typically incoherent, at least in the very first tries. And also the radiation is distributed between many modes, and that's a key point, that the efficiency of your collector is such that it does not extend over all spatial modes into which the atom can decay. As a result, there is a degree of freedom that gets entangled when you click two photons, which is polarization, but the two photons exhibit no correlation in phase by their own. So we have realized a system that consists essentially of a well-known superconducting artificial atom coupled to an open waveguide, in which the atom is driven coherently, and this is something we know how to do pretty well, and also it decays into individual well-defined modes. So what happens as a result of this operation is that the coherence that's stored in the state superposition of the atom is directly mapped into this well-defined photonic modes, which are itinerant photonic modes along the waveguide. As a result, if you look at it this way, in this extended Hilbert space consisting of the atom as well as the two itinerant modes, cascade decay is indeed a fully coherent process, which will lead to phase correlations between the emitted photons and to their entanglement. So this experiment, which we performed, naturally fits into a large class or family of experiments performed with superconducting circuits aimed at generating, manipulating, and detecting microwave radiation with superconducting circuits in the quantum limit and close to the single photon level. And this is a field that some people like to refer now these days as quantum microwave photonics. So I won't attempt to review this field here, of course, and hopefully nobody gets offended if their own work is not in this list. I will essentially confine myself to a few examples that directly deal with the generation and detection of single photons. So the first experiment for a single photon source in the microwave domain is probably this one from Andrew Houck in Yale. And it is essentially based on the fact that once we have good coherent control over a two-level system and we can control the environment to which it decays, basically we can achieve single photon generation by preparing the two-level emitter in the excited state and let it decay spontaneously into the mode we've selected. And this is what was done in this experiment. In many of these experiments, the setting looks like an atom or two-level system inside a cavity, and the cavity is coupled to an environment or a waveguide with a rate kappa. And now the fact that we can control, for instance, either the coupling rate to the environment or the coupling between the atom and the cavity itself in real time, as was done in these two experiments, makes it possible for us to shape the temporal profile of the photon and to move it essentially from a simple exponential decay into any decay shape that we're interested in. And this is particularly relevant, for instance, as one deterministic scheme for entangling remote qubits relies on the fact that the superposition of 0 and 1 photon is emitted from one atom and reabsorbed by the other, but the efficiency of the reabsorption strongly depends on our ability to shape the temporal profile of the photons. I also would like to mention another experiment along these lines that recently came out. It's an experiment where the rate of spontaneous emission is controlled in real time by changing the boundary conditions of a semi-infinite waveguide. Now, to characterize quantum microwave radiation at a single photon level, the community has relied mostly on linear amplifiers, and this is in contrast with the optical case in which single photon detectors or clicking detectors are typically used. When it comes to the quantum state tomography of a photonic field, these two approaches have shown to be largely equivalent. And this has allowed us to probe many quantum features of the radiation, including anti-bunching and indistinguishability of two emitted photons with linear amplifiers. One also has to mention that while in principle it's not required to have a quantum limited amplifier to perform these characterization measurements, it's just much easier to have one, and the development of parametric amplifiers whose noise is close to the quantum limit has, I would say, greatly helped this field, especially if you think of characterizing arbitrary photon correlations. The higher the order, the larger the amount of averaging that's required to get rid of the noise. And this is why it's better to keep the noise down as much as allowed by quantum mechanics. Still, I mean, it is a reasonable question to ask whether one can build a clicking single photon detector in the microwave domain. And people have been working on it, and perhaps the early example is from the Harosh group in 2007, where basically flying atoms across this cavity were shown to be sensitive to the state of the cavity at the single photon level. More recently, and moving to planar and more familiar architectures, there has been some attempt to catch a single photon using an impedance matched lambda system and essentially storing the state of the photon that is absorbed by this lambda system. In general, we know in this community we can do single qubit readout in single shot with fidelities these days routinely exceeding 90%. So it would sound like a good idea to map the state of the photon into that of the qubit and then read out the qubit with conventional techniques. And this is something we are also working on, and we have our version of the single photon detector, which we are developing. I would also like to mention finally another approach, which is based on the variation in the inductance of proximized S and S junction. When it absorbs a photon, the temperature changes, the inductance changes. And this was also proposed long ago by, at least in some form, by Giazzotto and others more than 10 years ago. And I like this realization in the Mikko Möttönen group from last year, where they actually use electrothermal feedback to enhance the ability of readout, and the readout in single shot pulses of around 80 photons, which is not quite much as one, but I think it's an interesting approach, even if, of course, it's very difficult because the energy that's deposited by a single microwave photon is orders of magnitude less than an optical one, and then this makes a calorimetric approach generally quite difficult. Okay, that said, let me turn to a brief outline of the remainder of this talk, and I'm going to show our two-photon source and the experimental setup we used to measure it. And then I'm going to describe the characterization of this source using continuous wave and pulses. Then some conclusions, and if time allows me, I would like also to show some further material that we have gathered by driving our two-photon source with much higher power and what the inelastic scattering spectrum look like of this system. And also maybe as a very final thing, point out to what my next experiment will be, and mostly to get some feedback from some of you in the audience who might like the topic. Our two-photon source looks familiar. Aside from the shape, it's probably the standard transmon many people have seen. A peculiarity of the system is that, contrary to other realization, it's not embedded in the cavity, but it's straightly coupled to two waveguides. And the two waveguides are coupled asymmetrically, so one is coupled very weakly, and it essentially acts as a charge line for the transmon, allowing for coherent excitation. And the bottom waveguide is coupled more strongly, and that's essentially the predominant decay channel for the source. We achieve a strong coupling to the forward port, meaning that most of the radiation goes to this mode with a radiative line width of the order of 2 megahertz. One reason we choose this line width to be small, Michel has mentioned that actually in these systems we get couplings as big as we want, is that we are looking at these photons in real time. So we want their temporal envelope to be slow enough that we can, with our digitizer, look at them in real time as a decay. This is a spectrum of the first three levels of the transmon, which is, as we know, an anharmonic harmonic oscillator. So the first two, transition frequency and the anharmonicity, is in the typical range for the transmon, around 200 megahertz. the way we're going to drive this source is by two-photon resonant excitation as this transition that many of you have probably seen in spectroscopy, and basically which will pump the system straight from G to F without passing via E. Upon this driving, the type of dynamics we expect is coherent pumping from G to F, followed by cascade decay into E and G via the emission of two photons at these two, close to these two bare frequencies. Now, the fact that these two photons do have a different frequency allow us in principle by appropriate spectral filtering to separate them and route them into two separate spatial modes. And this is something, maybe I still would like to acknowledge this work, which is based on a flux qubit, if I remember correctly, but it's still one of the first single photon sources that are in open waveguide and not just in a cavity. And one immediate advantage of this is that if your cavity has a fixed frequency, then you cannot tune the source emission. But in this case, the frequency is tunable. So essentially, by varying the single parameter, which is the frequency of the qubit, we can tune the frequency emission of the source, which is typically more difficult in a setup that includes a cavity. This is what our chip looks like, and we have essentially embedded our single photon source in this on-chip microwave switch that we developed in this work. The switch essentially has 4 ports and consists of 2 pi-half microwave hybrids and 2 tunable resonators here in green. It has essentially forwards all radiation to either port 2 or 3 when these 2 resonators are tuned to a common frequency. And then radiation that is within the bandwidth of these 2 common resonators is routed forward from port 1 to 3. And radiation that's off this transmission band is not reflected, but is actually routed still forward to port 2. If we look at what are the frequency scales for this object, we have designed the switch to have a transmission bandwidth of 100 megahertz. Our emission linewidth is about 2 megahertz, and the enharmonicity of the qubit is 200 megahertz. So we are essentially in a regime where the line width of the resonators is much larger than the radiative line width of the source, and it's still smaller than the enharmonicity. So this enables us to make a selective routing of the 2 photons, and essentially to route the G photon here and the EF photon there. Let's have a brief look at a simplified version of the experimental setup. Essentially, we use this port 4 as a probe to characterize the switch property, and relying, for instance, on some symmetries in the scattering matrix of this object. So it's essentially an independent probe port. Most of the action takes place here where the single photon source is. It's driven either continuously or by a pulse. And then the radiation is routed by the switch and collected by 2 nearly quantum limited parametric amplifiers. Then what we perform here at room temperature is essentially double heterodyne detection by mixing with 2 independent local oscillators and fast digitization with an analog to digital converter. I can show basic characterization of the switch using port number 4, and this essentially shows our ability to route radiation of the GE photon to the one port while at the same time keeping it away and routing radiation from the EF photon to the other port. And if we put these numbers together, we estimate that we route 91% of the GE photon and 85% of the EF photon to the intended port. And these numbers could probably be straightforwardly optimized by, let's say, increasing the enharmonicity or tuning down the band of the switch. That said, the first measurement we have taken is upon continuous excitation, meaning that we resonantly drive the 2-photon excitation and looked at the spectrum of inelastic scattering, which is essentially the power spectral density. The dashed line indicates essentially the bands over which we do probe the spectrum. And these bands are limited by a combination of our parametric amplifiers, which are tunable, and the further digital filtering that we apply. And we typically choose this combination so as to optimize signal to noise for the intended purpose. So we drive in the middle, and we see 2 single peaks at the 2 transitions that we ascribe to emission of 2 photons in a cascade. Of course, it doesn't prove now that they are single photons, and it does not prove yet that they are emitted in cascade. For this, we have to wait a few slides. First thing we did, we changed the power. So we studied this very same spectrum as in the previous slide for varying power. Power is increasing along the y-axis. And we see different features of these peaks. First of all, they increase with increasing power and eventually saturate. The integral of the power spectral density is proportional to the photon flux emitted into each channel. So the fact that there is an increase followed by saturation is to be expected for a three-level system, because the photon flux is eventually limited by the population of the excited state times the relaxation rate. We also see that these two peaks fan out as we increase the power, and this is a stark shift due to the presence of the drive. The solid lines are a global fit to all these data sets using master equation and input-output theory. It's a very basic three-level model for the transmon and the waveguide treated in the standard way. All the parameters we actually take from the spectroscopy measurements. So the only global fit parameter here is actually the total attenuation of the input line, which gives you the proportionality constant between the drive strength at the qubit and the input power at your microwave generator. Since we are driving a two-photon transition, the effective pump rate from G into F is not proportional to the amplitude of the electric field of the atom, but to its squared, because it's a two-photon transition, and this we have to keep in mind. So what I'm noting here for any individual input power is the corresponding effective pump rate normalized by the decay rate. I also want to mention that you can wonder what happens if you keep driving stronger, what happens in this region, and I will come back to this in a few slides. Then we turn to higher order correlations that are going to tell us something about the nature of the emitted radiation. In particular, a standard way of characterizing single photon radiation is to look at the autocorrelation of the intensity, which in our case it's an autocorrelation of the power. These are reported here for the two modes, and it actually does show that radiation consists predominantly of single photons, as can be witnessed by the fact that the power autocorrelation at 0 time is close to 0. Yeah, this is true, and I could tell perhaps more about it. What briefly, yeah, this is correct. And I think I can give both a short and a long answer. Maybe I'll try with the short one first and explain how our subtraction scheme works. It essentially, it's a subtraction scheme that's based on taking 4 measurements and interleave them very fast. And these 4 measurements are the power spectral density of the signal with the radiation on and off, and the G2 of the signal with radiation off and on. Now, if we assume that the noise is the classical noise, and that the signal and the noise are fully uncorrelated, we can deconvolve essentially these moments and measure what the G2 of the signal alone would have been in the presence of uncorrelated classical noise. So this would be the brief answer, so to say. But actually, it is not a single measurement. It's a result of 4 measurements. And of course, this subtraction scheme is based on subtracting 2 very big numbers to get a small one. So it's very sensitive, actually, to errors. And this is why, for instance, we interleave these measurements on a very fast time scale, because any drift, for instance, in the gain of our amplification chain will affect the result. So this is actually a very good point. And we're looking at a signal that is a fraction of a single photon. So it's a small signal on top of a large noise. There is one more feature, and then the black one is a theory, and the theory is essentially obtained by taking the purely theoretical G2 and taking into account the finite detection bandwidth by convolving it with the kernel of the filter function. This is an approximation that holds in the limit where the signal is small and the noise is large. And this is actually important, because the reason why this is smeared out is partly because of the action of the filter. There is also a qualitative feature that the theory predicts that doesn't look quite much like the single photon anti-bunching, which is the slope here is decreasing, while in the single photon anti-bunching, it just goes flat to 0. This is actually a real feature of the theory, and it comes from the fact that we are driving this two-photon transition, and there are little oscillations with the frequency of the enharmonicity, which is a much faster frequency. And basically, the filtering out of these oscillations close to zero gives rise to this behavior, which is in a way an artifact of our filter, but is predicted correctly by the theory. That's what I wanted to say. The next thing we can look at is to cross-correlate the two channels. And we study then the power cost correlations. And these are going to tell us something about the statistics of the arrival time of the two photons. We are looking first at this measurement at low power to see that these cross-correlation functions are strongly anti-bunched at negative times and strongly bunched at positive ones. This is just to be expected from the fact that the photons come in cascade. This large peak essentially tells that if we have just seen an EF photon coming, a GE photon will come next because of the cascade. And at the same time, these anti-bunching peaks tell that if an GE photon has just come, we need to wait until we see the next one because the system has to be pumped back to F before the next photon can be emitted. So this is typical statistics for a cascade decay, and indeed we can find references from the atomic physics where precisely this statistics was observed. A regime that's perhaps a bit more difficult to attain is a regime where the radiation rate is comparable to the drive rate. And this is a regime where now the picture qualitatively changes. And this is because now the pump rate is just as fast as the decay rate. So we can expect that after the system has decayed to the ground state by emitting a photon, a next photon can come because the pump is fast enough. And this turns into the developing of a super bunching peak also at negative times due to the combined action of the decay and the pump. And at high power, what happens is that we essentially have in the cross correlation, we have a profile that resembles the one of coherent oscillations with a frequency that has to do with the pump, with the rate of pumping from G into F. All right. Then to observe the phase correlations between the two photons and to generally look at these two photons one by one, we turn to a pulse excitation scheme. Pulse excitation means that we send a preparation pulse to the transmon that will prepare it into, ideally in a given superposition of the G and F states. And then we record in real time how these two amplitudes of the field vary. A technical note is perhaps that we do what we, in our jargon, we call signal math prior to ensemble averaging, meaning that we could simply average these values and we would get the average amplitudes, but actually we can perform this sort of multiplications at each instance and make the average only at the end. And of course, these two types of averages do not commute and allow us to measure not just the average amplitude, but for instance, the average powers, the amplitude cross correlation, and so forth in real time with a bandwidth that in our case is of the order of 10 nanoseconds. So here I present experiments on the time resolved powers versus time on the x-axis and the squared pulse amplitude on the y-axis. The reason why the pulse amplitude is square is again because it's a two-photon transition, and so you expect that the Rabi rate is proportional to the square of the amplitude. And the bottom plots are line cuts of the top plots along the dashed lines for 3 selected values of the preparation angle. And to ease the comparison between these two sets of pulses, I've also plotted one pulse from the right into the left and the other way around. The first thing we notice is that these time-resolved powers, they increase and then decrease. So there is this oscillatory pattern that reminds of Rabi oscillations. And then the peak is at the same position in both, which is also consistent with cascade decay because both the photon fluxes are going to be proportional to the same F-state population reached by the preparation pulse. We can also look at qualitative features of these pulses. We see that they are not quite the same. So these are really the temporal envelopes of the two emitted photons. And we can see that the GE photon is slower by a factor about 1/2. And this is just because of the matrix elements that couple the transmon to the waveguide. There is a square root of n as you climb the ladder of transmon states. The pulses for the G photon are also delayed by a time that's proportional to the inverse decay time from the F. And this is also to be expected because once we pump to F, this photon is emitted immediately, but the E state is initially empty. So this photon, before being emitted, has to wait until the E state gets populated. The next most interesting thing we can look at is the phase correlations between the two photons. And one way to look at them is to plot, for instance, the real part of the amplitude cross correlations and see that they emit, essentially, there is basically an oscillatory pattern. This cross correlation goes up and then negative, and this is it is a signature, a clear signature of strong phase correlations between these two. For comparison, one could look at the individual amplitudes of the two photons and find that they vanish identically within our noise level. And this means that if you take any of these two photons independently, they have no definite phase. It's just a relative phase that is locked by this experiment. So explaining this, it's not difficult if one is willing to accept this extended Hilbert state picture, in which now we have defined two itinerant photonic modes which have precisely the temporal shape of the two emitted photons. And then essentially, we start from this ground state. After state preparation, we manage to put the source in a superposition state. And after a two-step cascade decay, this superposition has been transferred to the photonic modes that have become entangled. For instance, for a preparation angle pi/2, the two modes are in the Bell state, 0 and 1. The one way to verify that this state has been attained is to do joint quantum state tomography of these two fields. And in doing so, we will use this temporal mode matching, meaning that we want to pick precisely these two modes that move in time. So what we're going to do is that we are going to essentially convolve our signal with a filter function that looks like the time-reversed photon shape. This is a result of such a tomography that is carried out using techniques that are described quite extensively in these papers. Essentially shows us all the first moments of the fields up to the fourth order. And it looks a bit like a jungle, but maybe we could look at selected moment first. The fact that the second order correlation vanishes tells us that we have to do with single photons. And this is a confirmation of what was obtained in the continuous wave measurement. Then the vanishing of the amplitudes, as we said, says that no photon has definite phase. And a large value for the amplitude correlation tells us the two photons are entanglement. The next thing we can do to plot this differently is that we can take this set of measured moments, we can take the standard deviations that, as you can see, increase with the order of moments, and try to reconstruct the most likely density matrix that in the joint Hilbert space of these two modes describes the state of the system. And this is what we have done here, truncating the Hilbert spaces to up to 2 photons per mode. What we find here is that we find, based on this reconstruction, a fidelity to the Bell state of 91% and a negativity of 0.43, which would signal a very strong entanglement. A disclaimer that we must do here is to say that these numbers are actually referred to the output of the switch. We have essentially taken out the inefficiency in our quantum measurement. And this efficiency we can reconstruct. It comes from a number of factors. For instance, part of the photons are emitted to the wrong port. There are going to be losses between the photon source and our amplifiers. We have a set of circulators and cables in between. And also there are going to be losses related to our temporal mode matching technique, which is not perfect. So we can independently estimate each of these loss, and we come to a quantum efficiency that is about 7 or 8% for each of the lines, which is a number that's slightly slower than we typically have. I think we routinely reach maybe around 20%, but this still tells that these numbers can look exceedingly good, but one should remind that the quantum efficiency of our measurement is not precisely 1. Okay, so in summary, for this experiment, we have looked at the cascade decay of a transmon while driving it with a 2-photon resonant excitation. And we have shown how preparing the source in a coherent superposition leads to entanglement between these two photonic modes. Is spontaneous emission an incoherent process? Well, of course, as I made this point in the beginning, I mean, provided you have full access to the Hilbert space that includes your environment, this is not true. Yeah, if the atom decays into a well-defined mode and you look at this mode carefully, you will find out it's a fully coherent process. And the fact that the way you look at photonic fields actually influences the dynamics is something that has been seen lately in a few experiments, including this one by Kater and others. This first version of this paper you can find on the archive. And now, if I still have a little bit of time, I would like to present, let's say, some bonus unpublished material that relates to the same system, just driven more strongly. I just remind here what the spectrum of the system looks like, the 3 relevant frequencies, and the decay rates. And now I'm going to ask you to guess what this plot looks like. It's a plot where on the y-x-axis we have the frequency at which we drive, and on the y-axis we have the frequency at which radiation is emitted. And there is at least one part of this plot which is rather easy to guess for somebody who has taken a course in optics, which is the familiar Mollow triplet. If we drive resonantly with the G transition and saturate the system, we are going to see a central peak and then 2 satellite peaks spreading away with a detuning proportional to the drive. But then, interestingly, we can also look at emission at the 2-photon transition, and then part of this emission was already discussed in this talk. We have seen 2 single peaks in these regions corresponding to cascade decay. And then one could also wonder, besides the coherent contribution to scattering, is there going to be some incoherent scattering also at the 2-photon transition? This we have to see. Maybe as a remark, the fact that there is nothing here relates to the fact that the system is typically in the ground state. If we put some population in the excited state, actually you do see a mirror structure appearing here, just for completeness. So we have done this experiment. We have driven around the 2-photon transition and looked at the spectrum of inelastic scattering at these 3 important frequencies. And this is an experiment that would look pretty much like the one we have just done. So 2 single peaks here, plus possibly a little bit of scattering at the GF2 frequency. And we are comparing experiment and simulation and finding, I would say, good semi-quantitative agreement between the two. If we increase the power further, we are going to see that each of these single photon peaks is split into a doublet, and there is a Mollow triplet-like feature appearing at the GF2 frequency, which is more clear in the theory than in the experiment. This is the reason why we have repeated the experiment on a different sample with a parametric amplifier, and I think we have good confirmation that it's indeed a triplet also in the experiment. This is cleaner data than the one before. And I think this is an interesting feature in optics. One way to look at this was done in spectroscopy. With two-tone spectroscopy in this paper, it was shown essentially that when you dress all the 3 states, you have a 6 spectroscopy peak, basically. Each of the single photon peaks splits into a doublet. And this is an effect that you reach when the drive frequency is close to the anharmonicity. It's something that's really peculiar to something like the transmon or something that's weakly anharmonic enough that you can actually reach this regime where a single drive actually dresses 3 states at once. It has also, I think, some interesting relation to multi-photon blockade in the Circuit-QED system, when you essentially hybridize your 2-level emitter with a cavity, which is a harmonic oscillator. You also get an anharmonic oscillator that you can, whose multi-photon physics you can probe. And here we found some, I think, a nice connection to one early theory work from the Carmichael group, and also some recent work from the Rempe group on multi-photon physics. I would also like to point out there has been lots of theory work, mainly from these people, on what sort of photon correlations you get if you apply frequency filtering to a photonic field. And for instance, I mean, one interesting question you can ask is that this is inelastic scattering at a 2-photon transition. Would it have a single photon or a 2-photon character? And this is something we could address experimentally. And should I make a guess? I guess it's 1 photon at a time. But I haven't proven it yet, and if somebody has a different opinion, let's talk. Okay, but this we could measure, right? I mean, with the spectral filtering technique in combination with time-resolved correlation functions. Okay, finally, very last thing. Not so related with what I've said so far, or partly at least. What my next experiment will be, I would like to study photon interaction in arrays of coupled cavities. And these coupled cavities are going to be based on lumped element resonators. We are going to add a transmon qubit with a full control and readout capability. And we are going to use source of microwave photons, single photon sources, biphoton sources, which we are developing, and parametric amplifiers to characterize them. And as I've also shown in this talk, we have many of the building blocks that are needed. And I've just put here a quick sketch of what a device could look like. It's an array of 41 cavity. They are nominally identical. There is one special cavity where we host a qubit, which we make frequency tunable, the same as our switch. And then essentially, we can probably look at a number of different things. This coupled cavity array is going to develop a transmission band, and we're going to place the atom in between and look at different things. We can do real-time experiment. We can do transport experiment, multi-photon scattering, and atom-photon bound states is something I would like to look at. And of course, I'm of course well aware that there is related work from Andrew Hauck, Dave Schuster, and I'm sure many people are looking at similar objects at this time. So thanks for your attention, and I'll take any questions.
Thank you, Simone. Can have some questions? Okay, was there a question there? Okay. Maybe let me start off. Maybe I missed something in your, at the end of the first experiment, you talked about your quantum efficiency, which was 0.07. So was that experiment not using parametric amplifiers, or what is setting that number?
Yeah, okay. Maybe I don't really need to go back there, but. So, as I said, a combination of 3 things. Mostly, I would say the switch itself doesn't have perfect routing efficiency, as I've shown. And then we have significant loss, perhaps a bit more than we typically do, in between the output of the switch and our first amplifier, which is a parametric amplifier. And so this, of course, we have, I think, either 3 or 4 circulators, and this is the loss between your signal and the first amplifier, as we all know, is a killer, right? So this is where we lose the most of it. Then, okay, one thing that there could be is that we are operating our parametric amplifier in a larger bandwidth and smaller gain, and this might bring in some contribution from the next amplifier, which is a standard Hampton amplifier. And then the temporal mode matching introduces another maybe 80% factor to this number. So 80%.
80.
85%. So these numbers are reasonably close to 1, but if you start multiplying them, you can get something surprisingly low.
I mean, because 0.07 just seems really low. I mean, even with 4 circulators.
Yeah, it's a bit lower. And there is one channel that's a bit better. It's above, I quoted the lower one, to be fair. One that's about 0.12.
Just to follow up on that, how do you actually calibrate how much is lost back into the drive port versus coming out the strongly coupled port?
Okay, so the one thing maybe should I come back to the picture? Okay, so the one thing that's rather easy to calibrate is how the switch routes the different modes. This we can use the probe port. Yeah. Right, but this is capacitive coupling, essentially. It's pretty easy to model. And I think it was actually verified in the previous paper where we studied single photon emission from this device, and things are a bit easier there. But essentially what we got is that it's a model number. I mean, capacitive coupling, I think we understand fairly well in these geometries. It's about 97, 98% goes forward anyways.
I was curious to know how does your experiment compare to what people are doing with semiconducting quantum dots, in which they are using by exciton and exciton cascade decay?
That's an interesting one, and I think it's. I think in these excitons, one thing that was probably difficult was, I mean, these were used as a source also of entangled pairs, and one thing that was difficult was to remove this degeneracy to get this entanglement going. And I think it's an experiment on a different architecture, but also uses two-photon coherent excitation. That's true. So in the end, it's a similar object, even if the goal it was looked at is perhaps a little different, because there the main challenge was actually to get the two excitation path degenerates in such a way that you could get the polarization entanglement. So I'm not sure they looked at, for instance, half excitation and entanglement between the two photons. They coherently excited to the F, and then they look at the polarization of the two emitted photons. So it's a similar experiment taken from a different angle.
Okay, any last question? Okay, if not, let's thank, there's one.
Maybe there's one?
Yeah.
As opposed to homodyne, you mean? I think I mean, from the experimental point of view, it's easier to filter out a various range of offsets by leaving the last stage of demodulation in the digital part. So it's mostly an experimental requirement.
Okay, let's thank the speaker again.